Before we begin, I'd like to acknowledge the traditional owners of the land on which we meet today. I would like to give my respect to their elders, past, present, and future. This is my student Haomin Chen's completion seminar today. The title of her talk is Linear Ballistic Accumulator Models of Confidence in Response Time. Now, a lot of you are probably familiar with accumulator models and diffusion models. Some of you may even be a little tired of it. I would like to say that these applications are pretty different. So the way people are usually used to thinking about them is as models of choice and response time. What this work presents on is extensions to confidence, which have been done a little bit, but not a lot. And I think one of the things that's really interesting about the work that Haomin has been doing is it explores a lot of the various ways in which we can think about confidence and how they can be generated in this framework. It also presents a lot of challenges because when you want to actually explain this three-way relationship, it gets pretty challenging. And there's a lot of interesting kind of little challenges along the way that Haomin will talk about. So yeah, take it away, Haomin.
Thank you, Reverend. So hi, I'm Haomin, and just to reiterate, I will be talking about my PhD project on linear ballistic accumulator models of confidence and response time today. So before we actually get onto talking about what exactly is confidence, I just wanted to make the task clear at the outset. So let me briefly walk you through how recognition memory and confidence is usually tested in a laboratory setting first. So okay. So in a typical recognition memory task, what you usually first see is a list of words to study. Then there will be some kind of distractor task or other kinds of delay. And then you will be shown a test list. And for each of the word on the test list, you will be asked whether you have seen this word before or not. And the answer to that question is, it depends, right? So first, it depends on whether or not the item is actually on the study list. So if it is on the study list, we call it a target. If it's not, we call it a lure. And then this question's answer also depends on whether you have the correct memory for the item. So in addition to asking you about old or new, we can also ask you to state how confident you are in that decision. And this can be measured using a confidence rating scale. And by using this scale, you can state either a high level of confidence or a low level of confidence. We can keep expanding the scale to include more levels of confidence. So an interesting question we could ask from this paradigm is, okay, so in a laboratory setting, we have the answer to tell whether the participants' decisions are correct or not. But then in real world, often the answers are unknown or delayed to be known. So is there a way to predict accuracy of our decision from things that we could actually measure in time? Well, a number of research has established that accurate decisions tend to be fast and of high confidence. A lot of works have been interested in either the relationship between accuracy and confidence or the relationship between accuracy and response latency. However, few of them have looked at how these three measures together can interact with each other. And a lot of computational models of accuracy tend to focus on confidence alone, but not latency. So there is a need for a unified framework to account for this complicated three-way relationship. Here's an overall big picture of my PhD project. To provide a unified account of the complicated three-way relationship, we want to test and compare different confidence mechanisms on a level playing field. And eventually, we want to apply our models to awareness memory paradigm. So this is important as the decision made in awareness identification are usually highly consequential. So this means that we really want to know whether the identification decisions are accurate or not. So awareness memory is a domain where signal detection models are common, but this model have no explanation for latency. And at the same time, research does show that response latency does give some extra information for predictive accuracy over and above that from confidence. So a model that can account for accuracy, confidence, and latency is needed in this domain. But there remains a puzzle in the awareness memory space, and that is where our first study fits in. So a key assumption made in the confidence models and many other accumulation models is that the target variance exceeds that of the lowest. While it has almost been unilaterally found in recognition memory that avoidance variability of the targets exceeds that of the lowest, some studies from the avoidance memory paradigm reported an opposite result, which is the greater lower variability. So before everything, it was necessary to understand whether the two paradigms are fundamentally different from each other, or that the mixed result could be explained due to some other factors. And we needed to see if this assumption here is correct or not before we start building up and testing our confidence models. So how evidence variability is usually demonstrated is through the ZROC slopes. And let me give you some more background information on what the ZROC slopes is and what the ROC are. So this needs to be understood within the signal detection framework. Basically, ROCs can be constructed by plotting hit rates and false alarm rates across different levels of bias. And if we turn the values into z-scores, we get the z-transformed ROCs. So the SDT model makes specific prediction about the shape of the ZROC slope, the ZROC curve, that it should be linear with a slope equal to the ratio of the standard deviation of the lower distribution to that of the target distribution. So if the targets and the lowers have equal variance, you will see ZRC slopes of 1. And when the variance of the target distribution is that of the lowest, you will see ZRC slopes less than 1. And this is a typical result found in many recognition memory studies. When lower distribution have the greater lower variability, you will see the slopes larger than 1. So this is the result reported from Haomin memory pattern and a short-term visual recognition task of Yoshimoto et al. So how do we understand such discrepancy in the results? How we dissect this question is by looking at what's different between those studies I just mentioned. So what we found is that recognition memory studies that usually report greater target variability, they typically use words as stimuli. While Haomin's memory and the visual recognition task that reported greater lower variability, they use non-word stimuli. So a key factor that might be responsible here for the mixed result could be the stimulus type. On the other hand, recognition memory studies typically use long-term paradigm. While Haomin's memory also share a long-term components when we use a sufficiently long delay, it has to be noted that they also usually involve a short study list or a short test list. Finally, the visual recognition study also use a short-term memory paradigm. So it's possible that either test of short-term memory or a short study list or a short test list might be responsible for the result of greater lower variability. So we wanted to manipulate both the stimulus type and memory paradigm to see what is exactly responsible for the observation of greater lower variability. We manipulated the stimulus type within subjects. So that means the participants in each experiment will experiment both words and faces. We then tested the short-term versus long-term paradigm through across different experiments. In total, we designed 3 experiments for this study. In experiment 1, we used a long-term standard list memory paradigm. So there were like longer lists and some delay between the study and tests. In experiment 2A and 2B, we used a Sternberg-style task, which was similar to that of the Yoshimoto study, but with longer lists in experiment 2A. So here in experiment 2A, we had like 6 item study lists, but in experiment 2B, we only had like 3 item study lists. One advantage of using the Sternberg-style task is that this kind of task is kind of similar to the Haomin's identification procedure. So this means that there is only one identification decision made during the test phase. Here is just an illustration of the experiments. So the test phase was pretty similar across all the experiments. We first present a list of items, which can be either words or AI-generated faces. What's different between the experiments is in the test phase. So in experiment 1, we show participants a test list. But in experiment 2A and 2B, we show participants only a single test probe. So the task for all the experiment here was to tell whether the participants have seen each of the test items before And in the meantime, they will need to indicate the level of confidence on the 6-point confidence rating scale. Here are the results of the slopes and intercept of the raw ZRC slope, the ZRC curves. So the blue bars here represent thesis, orange bars represent words. The most important message here is that all the slopes were smaller than 1. So you can see that they're all below the red dotted line. This suggests that greater target variability was found regardless of the stimulus type or paradigm we used. We complemented our analysis by fitting SDT models to individual participant RC data using hierarchical Bayesian techniques. The modeling results are shown as the stars and dots in the plots. So the reason why modeling is needed here is that RC data sometimes can be quite noisy, while hierarchical Bayesian models, they are typically resistant to noise and outliers. This means that we can get more accurate estimate of the variability by fitting SDT models. So the modeling results support our previous conclusion of new evidence for greater lower variability. This was demonstrated both by the parameter estimates of the SD parameters, with ratios all being smaller than 1, as you can see the stars and the dots are all below the red dotted line. And this was supported by model selection using WAC values. So in the model selection, we compared an equal variance SDT model to 3 versions of the unequal variance SDT models. So the first unequal variance SDT model was where we let the SD parameter to be freely estimated. And then the second one, we constrained the SD ratio to be larger than 1. And then the final one, we constrained the SD ratio to be between 0 and 1. And the model selection result did not favor the model variant that constrained the SD ratio to be larger than 1 in any case. So that means models that assume greater lower variability was never favored in model selection. So in conclusion, the difference in stimuli and paradigms may not be responsible for the reversal of the usually observed pattern of greater target variability. However, we are not suggesting here that the previous observation of greater lower variability was due to chance. Rather, it might be reasonable to assume that there might be something else that's responsible. But the most important message here is from this study is that after a few rounds of testing, the assumption of greater target variability still holds. This means that there is a good start for our confidence models. For research output, this study has been presented on one conference, and then it has been published in Memory and Cognition. Okay, so now back to our big picture here. We can now start to think about how our confidence model would be like and how to test them. So this became our second study. Recently, there have been an increasing number of computational models developed to capture the relationship among confidence, accuracy, and latency. But the problem here is that there has not been a consensus on how confidence can be derived. This has motivated our second study, where we are trying to make some direct comparison between the confidence generation mechanisms. So what are the current models of confidence? So on one hand, confidence can be treated as a multi-alternative decision-making problem, which means that each confidence option can be directly accumulated. The article models are examples of this. On the other hand, confidence can be products of other processes. So for example, it can be derived from a comparison of evidence strength between choice alternatives, and this is described by Wicker's balance of evidence model. Confidence can also be product of subjective time, so in which fast responses are probably more confidence. Alternatively, confidence can be product of an additional accumulation process after choice, but that is something that's only possible when choice and confidence are made subsequently. So as you can see, all these models are quite different from each other, and there remains a lack of consensus as to how confidence can be computed. Also, there has not been any direct comparison across all these different confidence computation within the same architecture. So in our study, we are trying to lay out a few different ways to model confidence, and we are trying to compare them in the same architecture. And we are focusing on simultaneous judgment of choice and confidence. So the top three mechanisms here we consider here are the most relevant to the single stage decision. And we ask the question, how well do each of them capture decision making? To answer that, we first need to set a fair comparison among them. That is, we need to make sure when we find any difference in the confidence models, it's due to the difference in the confidence computation itself, but not other aspects of the decision process, such as noise during the accumulation process. So we chose one of the evidence accumulation models, the linear ballistic accumulator, as the common framework for all of our models. The family of evidence accumulation model have been generally quite successful with RT and accuracy, but the extension to confidence from this framework is still in its infancy. So that is what we explore here. In LBA, as you can see, each decision alternative is associated with an accumulator. In each decision trial, evidence begins to accumulate from a random point that is sampled from a uniform distribution with height A. The parameter B here represents the distance between the heights of the starting point distribution and the decision boundary. Evidence accumulates with a drift rate V, and the memory strength of the item determines the mean drift rate, and higher drift rate will produce faster accumulation to the threshold. So when one of the accumulator reaches the decision boundary, it triggers the corresponding response. And the response time is determined by the time taken for that accumulator to reach the threshold, plus the non-decision time for encoding and responding. And as you can see, LBA does not have within trial noise. So this means that the race dynamics are determined at the point of initiation. There are a few advantages for using this LBA architecture. So first, the models will be much easier to fit. Second, it will be easier to generalize our models to any number of decision alternatives. And finally, by having cross-trial variability in both the drift rates and the starting points, we can capture the relative speeds of correct and error response as well. Okay, now a common ground is that what will each confidence model be like? Let's first look at confidence by derived accumulation. We call this model the confidence accumulator model. This model is pretty similar to the article models that assumes confidence itself can be directly accumulated, but instead of using diffusion processes, it uses LBA. So the main idea of this model is that confidence can be treated as a multi-alternative decision. Each stimulus here is assumed to be associated with an activation distribution that is normally distributed. The mean of the distribution is freely estimated, but the standard deviation is fixed to 1 to prevent identification issue. This distribution is partitioned into different bins to be translated into drift rate for the accumulators. The criterion here is freely estimated but fixed across target and lures. The partitioning here captures the idea that evidence for the adjacent alternatives should be correlated with each other. So for example, if the distribution is shifted towards the right, you will essentially get more evidence for old and then less evidence for new. So if we want to account for confidence, we can just treat them as additional alternatives. This means that all we need to do is to partition the distribution into more bins, and that corresponds to each confidence category. So the winning accumulator here determines both choice and confidence. For higher number of confidence options, we just need more bins and more accumulators. Okay, so that's all with the confidence accumulator. Then let's look at confidence by balance of evidence. The multiple threshold race model is proposed by Reynolds et al., which assumes that confidence is computed from a comparison between accumulators. So larger difference between the choice alternatives means higher confidence in that decision. So for a simple two-choice decision, this model is basically the same as the LBA model, but a key difference in the MTR is that we additionally allow the drift rate to be, the trial-to-trial drift rate for each accumulator to be correlated. This is unlike in the LBA where drift rates are usually uncorrelated. This means that when the drift rates are positively correlated, sampling a high drift rate in one accumulator is usually accompanied by a high drift rate in another accumulator. And when drift rates are negatively correlated, higher drift rate in one accumulator will suppress the drift rate in another. This mechanism allows the model to predict many different patterns, and I will come back to this point later. Another key difference between this model and the LBA is that it has additional confidence thresholds, which takes the continuous spanness of evidence and map it onto discrete confidence categories. So in each decision trial, the winning accumulator determines both RT and the choice. In this case, this is an O response. And how confidence is derived is by looking at the position of the losing accumulator here. So if he has not reached the confidence threshold, we say that there is a large difference in the evidence, and therefore we have high confidence. If the losing accumulator has crossed the confidence threshold, then this will be a low confidence response. This model is simpler than the confidence accumulator model in the sense that to account for higher number of confidence options, we don't need to include additional accumulators. Instead, we can just add more confidence threshold in. Okay, so that's all about the MTR. And finally, we have confidence by subjective time. So this model, we call it the timing model. With an all-new decision, this model is exactly the same as the basic LBA or the MTR without correlation. What is different is that the timing model captures a theoretical idea that time determines confidence by using an additional timing accumulator here as a subjective measure of time to calculate confidence. This has been done in some theoretical works like Simon et al. 2016, where diffusion model was used as an effective measure to get a sense of time that has elapsed in the decision. Again, the discrete confidence levels are mapped out by applying confidence thresholds, but this time the thresholds are applied to the timer, not to the decision accumulators. So when one of the decision accumulator wins, if the timer has not crossed the confidence threshold, then we call it a high confidence response. Otherwise, it's a low confidence response. And you can just add more threshold to account for more confidence options. So as you can see, the timer has no impact on the decision itself. It just affects the confidence decision. And faster response will naturally produce high confidence. An important point to note here is that the timer is not tracking the theoretical time. It's instead tracking your inner sense of how much time it has elapsed. So the reason why we use subjective time here is that it's because it allows for overlapping RT distribution across the confidence options. So in the model, this is achieved by the trial-to-trial reliability in the timer strip-free. So for two trials that terminate at the same times, as you can see by the blue and the black arrows, if they terminate at the same time, because of the reliability, they can end up in different confidence regions. So one end up in the high confidence region and another one end up in the medium confidence region. Similarly, two different trials, as demonstrated by the green and the black arrows here, if they terminate at different times, due to the reliability in the timer, they can still end up in the same high confidence region. So that's all for the timing model. So just a quick summary of the three models. The confidence accumulator is the one with multiple accumulators and assumes a competitive race among all confidence options. The MTR is the one that compares the evidence strength between choice options. And the timing model is the one with a timer and that assumes subjective time to reflect confidence. So before we get into details of my experiments, I just want to highlight a few high-order goals for each of the models in order datasets. So we are talking about what we expect a good model of confidence to be like. So first, the model should capture RT distribution for each of the confidence response. And this requires us collecting many trials to get good measurements. Second, the model should be able to capture individual reliability. So for example, in Radcliffe-Stein's 2013, they found some fast low confidence responses in some participants. And we did the same in our dataset. So it would be crucial for the model to fit different individual patterns. And third, evidence accumulation models are presumed to capture behaviors across a range of tasks and manipulations. This means that a good model of confidence should be able to do so as well. And finally, a good model should be able to recover its parameters. So the reason why we value the model's ability to recover parameters is that evidence accumulation models are often used for parameter estimation. And in our case, we want to separate drift rate from thresholds in understanding performance. And a good parameter recovery is crucial for making such inferences. So now we have 3 candidates. How can we test and compare them? So what we did was we put constraint on one of the mechanisms, and then we were trying to see if the 3 models differ in their predictions. So the first step we tried was to constrain the direct accumulation mechanism by manipulating the confidence rating scale length. So the confidence accumulator model treats confidence essentially as a multi-alternative decision. The classic way to constrain multi-alternative decision-making models is to manipulate the number of decision alternatives. So here we manipulated the number of confidence options within subjects, and we tested through a recognition memory task and a perceptual identification task. So basically, it was the same task across all the conditions, which only differ in how many options the participant were given to respond with. And here you can see the different scales we use in our experiments. We also included some difficulty manipulation. This is through wire frequency in the recognition memory task and discriminability in the visual perceptual task. So how this manipulation could potentially constrain the confidence accumulator model is that, as Higgs law suggests, RT will get slower as the number of alternatives is increased. But in the confidence accumulator model, increasing the confidence options basically increases the number of accumulators. So having multiple accumulators will force faster decision because you get greater chance to sample high drift rate, and this goes against the Higgs law. So we thought that we could challenge the confidence accumulator through this paradigm. We also tested the model on how well they recover their parameters. But just a spoiler alert, the confidence accumulator model actually does quite well for the RTs. So this may be because the speed up is balanced out by the way evidence is partitioned. So here's a demonstration. When you go from 2 to 6 choice options, you are not just having more accumulators that speed things up, but at the same time, you are also partitioning the decision evidence into more and smaller bins. This might slow things down again, so this kind of balance things out. This experiment also provides a validation test for all of our models. So when the models are trying to capture changes across scales, there are all kinds of parameters that they can vary, but the parameters that represent memory strength should stay constant because there's no sensible reason for why how strong your memory is should be changed by what kinds of scale you are using. So let me briefly walk you through how what are the key parameters in each model. So in the MTR, the drift rate is determined by the memory strength of the item. So drift rate are the key parameters that should stay constant. In the timing model, again, the drift rate are the drift rate. The key parameters are the drift rates. In the confidence accumulator, things are a bit different because now memory strength is represented by the activation distribution. And remember when we compute drift rates, there is this scaling parameter here in the equation. So as the sum of all drift rate is just the integral of the activation distribution, scaling the drift rate differently will largely change the sum value and therefore suggest a very different level of activation. So the key parameter in this model should be the scaling parameter here. Okay, now let's move on to experiment and results. So in study 1, we did 2 experiments. Experiment 1A was a recognition memory task using standard list memory paradigm. So it's worth mentioning here that in the recognition memory task, we are still finding greater target variability in the parameter estimate. So this links back to my study 1's conclusion. Experiment 1B was a perceptual identification task using a simile we call it the flash increase, and here's an example. So the reason why we included multiple tasks here is that to provide a test to see if the models can capture different behaviors. And we don't expect different tasks to produce the same kind of pattern because our goal here is not to understand why there would be any difference in between different tasks. It's just that the task may cause different problems for the models, and we want to see if the models are flexible enough to be applied to different tasks. We had 32 and 40 subjects in the 2 experiments, respectively. The experiment was conducted over 3 sessions, and we collected a large number of trials. For computational modeling, we again use the hierarchical Bayesian techniques to fit our models. And just to show you a demonstration of the experiment design. So this is for experiment 1A, the recognition memory task. We use a standard list memory paradigm where you get to view a study list first, with words presented one at a time, then destined the structure task. And finally, you will get a test list where you need to tell whether you have seen each of the test items before using one of the 3 confidence rating scales. And here's a demonstration for the design in experiment 1B, which is the perceptual identification task. Because it's a perceptual task, there will be no study phase, but just the test phase. So the task here was to tell whether there is more orange or blue in the flashing grids using, again, one of the 3 confidence rating scales. Our model selection using the WSC values, they were the confidence accumulator model in experiment 1A, and then if they were the MTR in experiment 1B. So in the following section, I am going to present some results from both experiment 1A and 1B together, and I will go in this order. So I'll first talk about the overall results in each condition, then I'll talk about the confidence accuracy relationship, and then the confidence RT relationship, and then some individual fits. So let's start with some overall results. For the results, we found that longer scales were associated with similar accuracies, but longer RTs. We examined how well each model captured this overall accuracy in RT in each condition. So the black dots here represent the data, right? And the color stars will represent model predictions. The green stars are the MPR model, the blue stars are the timing model, and the red stars are the confidence accumulator model. So in experiment 1A, you can see that all models perform reasonably well in capturing both accuracy and RT data. But in experiment 1B, the confidence accumulator model, which are the red stars here, is really missing the 4 choice and 6 choice condition for the overall accuracy. And this is why it was not preferred in model selection of experiment 1B. So this means that the confidence accumulator model is already at this disadvantage because it cannot capture multiple tasks. So in the next part, we break things down to different levels of confidence. A main question we ask in our study is whether the model can capture the relationship between confidence, accuracy, and latency. So we want to first look at how well the model fit the confidence accuracy data. So for a 2-choice task, the fits are pretty similar because all models are just very much like the basic LBA. In the 4-choice condition, you can see that low confidence responses are less accurate than high confidence responses. And all models were able to capture this positive relationship between confidence and accuracy. In the 6th-choice condition, again, you see this U-shaped curve. And again, all 3 models did a reasonable job here. Remember, this is the result for experiment 1A. In experiment 1B, things are a little bit different. So you can still see similar model performance in the 2-choice condition and the U-shaped curve in the data for 4-choice and 6-choice condition. But this time, although all the models can still capture the positive confidence accuracy relationship, the confidence accumulator, so the red stars again, always underestimate accuracies in the 4-choice and 6-choice condition. So this is again the reason why this model was not preferred in model selection of experiment 1B. In addition to confidence accuracy relationship, we were also interested in whether the model were able to capture the relationship between confidence and RT. We examined the complete RT distribution and we summarized the RT distributions by the 0.1, 0.5, and 0.9 quantile. So again, in the 2-choice condition, the fits are quite similar. In 4-choice condition, you see faster RTs for the high confidence responses. The 3 models were able to capture the negative confidence RT relationship. In the 6th-choice condition, you see this inward U-shape again. And generally speaking, the 3 models all fit reasonably well for RTs. So one thing I want to point out here is that, especially in the 4th-choice condition, you will see some 0.1 quantile shifts across the confidence levels. This was not that obvious in experiment 1B. The Articon 2 model was developed because the original Articon was not able to capture the shifts in the Pullman quantile. But as you can see, our confidence accumulator model can, and it does a pretty well job here. So this is because, like Articon 2, when estimating decision thresholds, our confidence accumulator model also tend to produce the same shape in the threshold as the Pullman quantiles. And this has an important implications that I will talk about this later. Unlike the fit accuracy, we do not see much a difference in model performance across experiment 1A and 1B. So in the data, again, you see similar performance in the two trust condition, and then the inverted U shape in the data. And then overall, in both experiment 1A and 1B, all three models perform quite well in fitting the RTs. You may have noticed from previous result that I've shown you that there are some puzzles remain unresolved. So for example, the model selection in experiment 1A favor the confidence accumulator model, but then we did not see much improved fits from the group averages. Also, the model selection in experiment 1B favor the MTR, but then although it's clear why the confidence accumulator model lose the selection, but it was unclear why the timing model was also not preferred. So because it does seem to do quite well in the group average plots. So this is where it becomes important to examine individual differences, because a model that does well on group averages may not perform that well for individual participant level performance. So for experiment 1A, we examine the models on how well they capture participant level performance. So what we did is we plotted individual subjects observed and predicted mean odds against each other as scatter plots. So if they correlate well, that means the model is able to capture both group level and participant level performance. We found that the confidence accumulator model generally performed better in capturing participant level performance. And we found the same thing here with response proportions. So I also want to point out that such advantage of the confidence accumulator model was not that obvious in the other two experiments. So this may have explained why this model was only preferred in experiment 1A. In experiment 1B, we examined each individual subject fits, and we found that there are some subjects that are poorly captured by the timing model. These subjects are the ones with fast low confidence responses. As I mentioned, Reynolds' 2013 paper also reported some similar subjects. So here you can see that these subjects here are showing some U-shaped ordered curves, and both the MTR and the confidence accumulator were able to capture this shape. The MTR does this by having the drift rate to positively correlate with each other. The confidence accumulator model does this by having the same shape in the thresholds. But the timing model can only predict the inverted U-shaped curve, which is the usually observed pattern, because its core assumption is that fast decision should be more confidence, and it does not allow for drift rate to be correlated. So this is why it was not preferred in model selection of experiment 1B. In addition to examining the model fits, we also examine validity of each model, and that is whether they produce sensible parameter changes. To do so, we fitted a set of new model variants that additionally allow the key parameters that represent memory strength in each model to vary across conditions. To do so, for the MTR model, the mean drift rate here, you can see they are pretty similar across the conditions, and the error bars are overlapping with each other. So the MTR did not require any change in the drift rates to capture the data well. And this is different to parameters like the decision threshold, which was really affected by the manipulation. And this was necessary to explain the slowdown in the RTs. For the timing model, again, you can see that the drift rate are not varying by much. For the confidence accumulator, the drift scale parameter also stay quite constant across conditions. But this is the validation test for experiment 1A. So in experiment 1A, all models have passed the validation check, but this is not the case in experiment 1B. So again, the MTR and the timing model, they did fine here. As you can see, they had similar drift rates across condition. However, for the confidence accumulator model, we see a difference between the 2 choice and the 4 and 6 choice condition. This variation is not sensible because using what kinds of scale should not affect how strong your memory is or the activation level of the stimulus. So the reason why the confidence accumulator requires a change in the drift scale in experiment 1B but not 1A is because the RT distribution was relatively flat, especially in the 0.1 quantiles. And a confidence accumulator model tends to produce the same shape in the thresholds as the RTs. This means that the model cannot rely on high threshold in each condition to produce the slowdown in RTs. This forced the models to scale the drift rate differently in order to capture the slowdowns in RTs across conditions. In addition to all the experimental tests, we also assess parameter recovery for each of the models. So an advantage of our study here is that we can directly compare the models on their ability to recover parameters. So generally speaking, all 3 models here, they seem to do a reasonable job. And the confidence accumulator model really surprised us here because it has a lot of parameters, but still recover them well. Same thing here in experiment 1B, all models recover their parameters reasonably well. So for an invariant summary, the confidence accumulator model was really challenged by our experiment 1B. Although it recovered the parameters well, it did not capture the accuracy data and it failed the validation tests. So the second step we took was to constrain the timing mechanism this time by manipulating speed accuracy emphasis. So basically what the timing model suggests is that if you respond more quickly, you are more confident. So if you force people to go quickly and sacrifice accuracy, the timing model will make a counterintuitive prediction that people will be more confident, which is probably not the case. So in study 2, we only did 1 experiment, which was a perceptual identification task again, and we used the flashing grids again. We had 30 subjects. The experiment was conducted over 3 sessions, and we collected a lot of trials. The task was to tell, again, whether there are more orange or blue in the flashing grids. So for this experiment, we only used the 4-point confidence rating scale. But what we varied was the instructions and feedback that were given to the participants. So like experiment 1B, the MTR won the model selection. The manipulation was successful with the accuracy emphasis associated with higher confidence, higher accuracy, and slower RTs. This is compared to the speed emphasis condition. To compare between models, we first look at mean confidence because that's what we expect to be diagnostic to differentiate between the models. So what we found was that all models appeared to fit the data reasonably well. And we were surprised to see that the timing model did not overestimate mean confidence here in the speed condition. A possible explanation for that is that the variation in the confidence threshold compensates for this. So the threshold varying assumption is somewhat plausible, as you can imagine the participant when they know that they are forced to respond quickly, they might strategically adjust how they map confidence to how they map time to their confidence. So the result here also goes against some previous result in the Vandenberg et al. 2016 paper that have argued that time alone cannot explain confidence. And the key difference here is that we use subjective time and they use veridical time. We also check model fits to overall accuracy and RTs. Again, you can see that the red star, the confidence accumulator model is misfitting a bit in the accuracy data. So this again explains why it was not preferred in the model selection. So it comes down to the same question that we don't know why the timing model was not preferred in the model section because it does seem to perform quite well for group averages. So like what we did in experiment 1A, we examined the models on how well they capture individual differences. We found that the timing model, so the blue ones here, is struggling a little bit for the high confidence responses under the speed emphasis. So we took a closer look to see where the timing model is struggling. We found some diagnostic subjects who had either an U-shaped curve or a quite flat RT distribution. So you can see the first subject here at an U-shaped curve. The other two subjects had a quite flat RT distribution. So both the MTR and the confidence accumulator model is capable of producing both the U-shaped curve and the flat curves, but the timing model always predict a large difference between high and low confidence. So this is why it was not preferred in model selection. For model validation check, we again fitted a new variant of the timing model, just the timing model, which allowed the time and drift rate to vary across condition. The timing model again passed the validation check as the time and drift rate was only minimally affected and error bars were overlapping. So this reflects the fact that your inner sense of how much time that has elapsed should not vary based on what kind of emphasis or instructions that you get. For parameter recovery, again, all models did pretty well here. So the main takeaway message for our study two is that although there have been claims that these mechanisms are all very different from each other, they do seem to behave quite similarly in many ways. But then when we examine from various different perspectives, the balance of evidence mechanism, which is the MTR model here, seem to perform slightly better than the other two models by having both the flexibility in capturing different patterns and producing sensible parameter changes. For research outputs, this study has been presented on 4 conferences. And finally, I want to say thank you to my supervisor, Eden, here for all his support through this long journey. And also thank you to my co-authors and my supervisory committee and all our members in our computational memory lab. And also thank you to my friends and family.
So this is very, very clearly explained, especially for someone like me who doesn't do decision models. I actually understood it, I think. I was wondering, so the MTR, so this is all for a binary decision of old new. And I was wondering, and I can see how the other ones might be extendable to like more than a binary decision. But how would you do that for the MTRs? Are you just comparing it to like the one you chose to the next closest, or like what's, yeah, have you thought about how that might, what you might do and what that might mean in terms of its performance?
That is a really good question, and that's kind of like a next step for the project, but maybe not for my PhD because we don't have enough time. So for the MTR, now we only have, so for a high enough of choice alternative, say like 3, we can just have 3 accumulators that correspond to each of the choice option. And then how we determine confidence, this can be done through a few different ways. So one is that you can count the threshold that's caused by all the losing accumulators, or alternatively, you can compare it with the second best accumulator. So it depends. There are like all kinds of ways that this can be done. As you said, this will be much easier for the timing model to do because you only need the timer to calculate the confidence. But then it will be a problem for the confidence accumulator because you will need a lot of accumulators to capture a large number of choice alternatives. Does that answer your question?
Yeah.
Maybe I missed this during the presentation, but if you output the response with they have the scale, right? Do they, for the reaction time recording, do they press a button and then do the rating, or do they choose one of the options and that's reaction time?
It's the second one. So they have a scale that's like definitely old, maybe new, definitely new. So they only make one decision and they click only one button that indicates both the choice and confidence at the same time. And that's when you recall the artist when they click that button.
You have to learn something if you do it slightly different, where you actually ask them to kind of respond as soon as they know, and then they do the rating, or do you lose that information that connects the reaction time to the confidence?
I guess you are suggesting the dual stage decision, which is when the choice decision and the confidence decision are made like subsequently or at different times. So we focus only on the single stage decision, which is the simultaneous judgments in our study because it's simpler. For the dual stage decision, it's possible to extend our models to it, but then there will be some other complicated patterns to capture. For example, like a response reversal. So people may have favored one of the choice options when they make the choice decision, but then they might change their mind when they indicate a confidence.
Maybe I can ask differently.
Yeah,
Do
sure.
you expect that you'll gain more information if you do the dual stage compared to the single stage?
Oh, that's a good question. So some dual stage model will assume that you actually accumulate. Oh, by information, I guess what you mean is in the decision itself, or
Yeah, like in the motivating example with the eyewitness lineup, if you'd have to choose which one which one should we use?
for our models, I will probably still choose the single stage decision, because if you apply a dual stage decision to our single stage model, it will be hard to determine when they make that decision, the choice decision, before they make the confidence decision. And I guess it'd just be a problem for us to know.
There's a question online from Daniel.
Oh, yeah.
Do you want to see if we can hear you, Daniel?
Hello, hopefully you can hear me. Yeah, thanks for an amazing comprehensive talk. And really interesting to see that the speed accuracy trade-off manipulation didn't differentiate between the models as much as I thought it would. I guess I have a question, and maybe this is asking you to speculate, but the participants who had the faster low confidence responses, that U-shaped curve was really interesting, because as you know, at the group level, if you sort of RT bin confidence levels, usually the fastest responses can be the least accurate, but they're the most confident, or, you know, at the group level. Did you have any indication of how, if the way they were doing the task was sort of comparable, or anything about those participants that produced that really interesting and diagnostic pattern? Or do they otherwise sort of look fairly similar?
I guess for that question, so we are not quite sure why they may perform in those ways. My only guess is that when they are forced to respond quickly under time pressure, people may engage in some kind of guessing, or they may engage in some kind of consistent pattern of pressing one of the confidence keys. So that might have produced the pattern. But then so if you are looking for like a theoretical reason, all of our models have some way to explain that. So for the NTR, is by the positive correlation. For the timing, this can be possibly done by using a mixture model of the reverse and forward timer. So we haven't done that yet, but it's a possible solution for the model. And for the confidence accumulators by the thresholds. So if you are looking for like a theoretical reason of why such pattern is produced, this model may have provided some explanation, but then I guess it's always hard to explain why there are like some individual differences, and it's hard to develop a theory of explaining individual differences. I don't know if that answers your question.
Yeah, sometimes people are weird. No, that was fantastic. Thank you.
Thank you.
Philip also has a question online.
Oh, yeah, sure.
Thanks, Haomin. Can you hear me?
Yeah.
Yeah. So look, thank you for a very polished and very sophisticated presentation. I've got a question about theoretical foundations, that you have developed your confidence models in the framework of an LBA, which is, as you highlighted, is a deterministic accumulator framework. And so all of the stochasticity in behavior is actually present at the start of the trial. That's the essence of the LBA. So it was really a question of how you can think about the flashing grids task, which is a decision about a stochastic sequence, which is stochastic in time, how you can think about that decision task in an LBA framework.
I guess, do you mean by how do we capture the noise in the
Well, yeah, well, I put more simply, the nature of that decision task, because it's a form of expanded judgment task, is a noisy sequence of within trial noise, but how you think about applying an LBA, which is a deterministic growth model, all of whose stochasticity is present at the beginning of the trial, and how you can think about modeling that kind of flashing grid task with an LBA. It's not obvious that they map onto one another very directly.
Yeah, that's a good question. And I guess for the LBA, it will be a little bit hard to capture the within choice because it doesn't have the components. But then for our specific flashing grid stimuli, you can see that although it's changing all the time, at the very first frame, you can already see, you can get an already overall idea of which portion is larger. So I guess that will kind of make sense for our
So
determine.
would the strong prediction be that you would get exactly the same performance with a single frame of that task and a dynamic sequence? You know, is that the implication of the LBNA analysis? That, you know, a single frame is containing all of the information used to make a decision? You know, it's a very strong claim.
Yeah, I guess that's what we have to suggest for that
Yeah.
claim. But then the reason why we chose LBA, not the other like diffusion model, is because we thought LBA is really simple and tractable.
Yeah, I can see there's a big tractability argument for doing this kind of project with an LBA, and you know, I have no quarrel with you using the LBA as a general framework because you've got very complex models. It was really about just the applicability of an LBA to the flashing grid task. Yeah, I would have been inclined if I was working in an LBA world to have used the stimulus, which was a static rather than a dynamic stimulus.
Yeah.
So, thank you. That's not detracting from the other aspects of your presentation. But I have an ongoing quarrel with the LBA, as you know.
Thank you for the question. And
So we're stop clock.
Yeah, so it's going on, thank you.
thank you for coming.